Hello, everyone. Welcome to Physics Lab. So this is Lab 2, which is going to deal with one-dimensional motion. Basically, it'll be the motion of a cart on an air track, and it will be undergoing constant velocity motion and constant accelerated motion. And then the second part of the lab is going to be graphical interpretation. So I've created these sort of idealized graphs that I want you to analyze, and we'll do some practice graphs so you can see how to do that. And then in your lab handout, there's a bunch of exercises for you guys to do, graphs for you to interpret, and so on. Now, the lab for all three classes, again, the Physics 206 Sports Physics Lab, 207 Physics and Movement Science Lab, and 212 General Physics Lab. This lab is again very similar for all three sections, so I'm just going to do one video lecture. However, there's a few questions that Physics 207 and 206 do not have to answer. Physics 212, general physics, will do the entire lab. So I'll describe everything there. But what I'll do, and let me just show you this, if the questions don't have anything written next to them, like question 1, question 2, and so on, that means all three labs are doing all three questions, or all these questions. And then we may get to a question, so like question 6, only Physics 207 and 212 are going to answer that. So Physics 206 doesn't have to do this question, and so on. There's a few more in the second part. Actually, the first 6 questions are the same for the second part. All three labs will answer them. And then after that, this question, only 207 and 212 will answer. Same thing with the next question. In this case, it's labeled 14. This one, and then actually the last few questions, it's just going to be Physics 212. Okay, so the classes are a little bit different, so you're answering slightly different questions, but the main idea is the same for all three labs. All right, let me go back to the beginning. Okay, so first thing I want to do is I want to define a couple of things. So I'm going to do this on the iPad, but let me just mention it here first. So the first concept is something called average velocity, and it's basically the average rate of change of position over time with respect to time. All right, let me explain this on the iPad. Okay, so let's say we have a cart, or an object, and it's moving on a horizontal air track. And let's say it's moving to the right. And initially, it's at some initial position. I'll just call it xi for initial. And then later, it's at some final position. I'll call it x final. And when it's at the initial position, there's some particular time. So I'll call it t initial. And then at the final position, there'll be a new time t final. So we want to calculate what the average velocity is when the cart undergoes that change of position. So by definition, the average velocity, I'll call it VAV, it's equal to the final position minus the initial position divided by the final time minus the initial time. So that's the definition of average velocity. And we can write this more efficiently using mathematical notation. So remember, if you have a change in the quantity, so final minus initial is a change in quantity, we can represent that by using the delta symbol. So I can call this delta x over and then delta t. So the average velocity is going to be the change in position, right? Change in x over the change in time. Okay, much of what we want to do in this lab is to interpret graphs. So even with this first part of the experiment with the cart and the air track, ultimately we're going to be making graphs on Pascal capstone and interpreting those graphs. So let me describe like what a graph typically would look like. Let's say we have let's say I have position I'll do centimeters on the y-axis and in time in seconds on the x-axis. And let's assume that the graph, the position versus time graph, happens to be linear. Okay, so it's like this. Okay, so since it's linear, one thing I could do is I could compute the slope, right? I could pick some point on that line, let's say this point right here. So this would correspond to say, you know, I'll call it T1, and then X1. So that time corresponds to that position. And then say over here, this would be T2, which corresponds to X2, okay? And now if I compute the slope, well, the slope is gonna be the rise, which in this case is the change in the position, right? So this will be delta X. It's gonna be X2 minus X1 over the run, which is the change in time. So the slope is equal to delta X over delta T. But we just defined delta X over delta T. Remember, that is the average velocity. So the slope in this case happens to be the average velocity over that time interval. Okay. Now, again, this is just an average, right? It's an average from T2, or sorry, from T1 to T2 over that time interval, right? The average over that time interval. What you might be interested in as well is not so much the average velocity, but you might want to know what is the instantaneous velocity at some time. Let's say I want to know right at this time right here, I'll call it T3. What is the velocity of the object right at that instant? How do I determine that graphically? Well, what you would do is you would go to the curve. So I'm going to go up to the graph. And then I would draw a tangent line to the graph at that point, which in this case, since it's already linear, it's going to be the same slope, right? So something like that. And then the slope of that little tangent line, that's going to be the instantaneous velocity at that time. If I want to know it at a new time, let's say I want to know it at, say, here, T4, I would go up to the graph. I would draw a tangent line and calculate the slope of that tangent line at that instant. And that would be the instantaneous velocity at that time. And so on and so forth. I could do it any time here. Now look what's happening in this case. What's true about this slope, the slope of that line segment, that tangent line, they're all the same, right? The slopes are exactly the same. Therefore, in this case, what this tells you is that the velocity is constant, right? The velocity is not changing. That instantaneous velocity is constant throughout. In fact, it will also be equal to the average velocity over this time period, right? It's the same, it's constant throughout. So this is very important. When you have a position versus time graph that's linear, it represents constant velocity motion. So let me write that somewhere. A linear position versus time graph represents constant velocity motion. Oops, constant velocity motion. Okay, because the slope is not changing. That's what it's saying. Let me fix this. So constant velocity motion. All right, so that's a linear graph. What if your graph is curved? What if it's like quadratic? Let me do the quadratic case. Actually, I'll go to a new page and do this. So now let's say I have position, say in centimeters versus time in seconds. And let's say it's parabolic. Let's say it does this. Okay, so what I could do is I could again calculate an average velocity over some time interval. So in other words, if I pick, say, this point right here, which is, say, T1, and it corresponds to this position X1, and then let's say I pick a point right here. So this would be like T2, and this corresponds to X2. And I calculate the slope of the line that connects those two. So let's say this is the line that connects those two. Well, that would be the same as before, right? It'd be delta x over delta t, because this is my change in x, and this would be my change in t. So the slope of that secant line that connects those 2 points, that's going to equal the average velocity, but it's going to be the average velocity over that time interval. Okay. It turns out the velocity is actually changing in this case, and I'll explain that in a second. So it's changing, but if you want to know the average over that time interval, it would simply be the change in the position over the change in time, right? So basically it's the slope of that secant line. Okay, but let's say we're not so interested in the average velocity. We want to know what's happening at an instant in time. So just like before, it's very similar. If I want to know, say, the velocity right at this time right here, let's call it T3. I go to the curve, I draw a tangent line, which means it's basically a line that just touches the curve at that point. And the slope of that tangent line is going to represent the instantaneous velocity at that point in time. If I want to know it, say at this point right here, I would go to the curve, draw a tangent line, and the slope of that tangent line represents the velocity at that instant. If I want to know it here, I draw a tangent line, and the slope represents the instantaneous velocity at that instant. Now, in this case, so where we have this, this quadratic function, right? This parabola, basically. What's happening with these slopes? They're increasing, right? So this is, in fact, at the beginning, it's almost zero. It's almost flat. Then it's a small positive, more positive, more positive. So therefore, in this example, you would say that the velocity is increasing over time. Okay. Now, it's not obvious how it's increasing over time. It turns out if this is truly a quadratic function, right, if it's truly a parabola, a quadratic function in position versus time, then it turns out the velocity is increasing linearly over time. That's not so obvious unless you know the math, the calculus behind it. But for our purposes, we can definitely tell that since these slopes are increasing, we know the velocity is increasing over time. So write that down here. So the velocity, by velocity, I mean the instantaneous velocity, is increasing over time. Okay. Second definition. Let's say I have the cart again. Let's say it has some initial velocity. It's moving in the x direction. I could write it as, I think I used Vx as my notation, Vx initial, and then at some initial time, t initial. And then later, let's say it has a new velocity. Let's say Vx final, and let's say it's larger, right? So it gets faster, and this would be at some final time. So since there is a change in velocity in the x direction, it means that there's an acceleration, right? In this case, in the x direction. Anytime you have a change in velocity, you're going to have an acceleration. So what we could calculate is what's called the average acceleration over that time interval. And the definition of that is the following. So I'll call it A average. It's going to be the final velocity minus the initial velocity divided by the final time minus the initial time. Or if I want to write it more efficiently, I can say it's the change in velocity. I'm really doing x because we're only moving one dimensionally, right, in x direction. So change in velocity in x direction divided by change in time. So it's kind of analogous to what you had before, right? Remember, average velocity is the change in position, delta x, over change in time. And an average acceleration is the change in velocity over change in time. Okay, what does this look like graphically? Well, let me go to a new page. So in this case, let's look at a graph of velocity versus time. And let's assume that it's linear. So I have velocity. This could be, say, centimeters per second. It could be meters per second. I'll just use centimeters per second versus time in seconds. And we're going to assume that it's linear. Okay, so again, one thing I could do, since it's linear, let's calculate the slope of this. So I'll pick a point on the graph. This, say, corresponds to T1. And let's say this is V1. And I'll pick a point over here, say T2, corresponds to V2. So then if I want to calculate the slope, well, it's going to be rise over run. But in this case, the rise is my change in velocity. And my run, again, is a change in time. So the slope is equal to change in velocity over change in time. But we just defined what that was, right? That is the average acceleration. So the slope is really the average acceleration, but it's over this time interval. Okay, so the average acceleration over that time interval. All right, now what if I want to know the instantaneous acceleration at some time? So this is analogous to what we did earlier, right? When we wanted to find the instantaneous velocity. If I want to know the instantaneous acceleration at some time, let's say I want to know the acceleration right at this time, call it T3. You go to the velocity versus time graph. You draw a tangent line to the graph right at that point. Well, again, since it's linear, it's going to be the same slope. So the slope of that little tangent line, that's going to be the instantaneous acceleration at that time. If I want to know it at, say, T4, I go to the graph, draw a little tangent line, and the slope of that tangent line would be the instantaneous acceleration at that time, and so on and so forth. Right? I can do this at any time that I want. Now, in this case, right, where we have a linear velocity versus time graph, what's true about all of these slopes here of these tangent lines? All the slopes are the same, right? So that means the acceleration, the instantaneous acceleration is the same, which means it's constant. So this is really important. So if we have a linear velocity versus time graph, it means we have constant acceleration. So a linear velocity versus time graph represents constant acceleration. Okay, now there's going to be one other thing that we need. Let me go back to the handout for this part. Okay, and actually most of what I mentioned is also in this handout, so you can look at the handout. I talk about, again, we can kind of quickly review. If I have a linear position versus time graph, that means I have constant velocity, right? So constant velocity motion. If I have a quadratic position versus time graph, it means that the velocity is changing, right? Because the velocity would be the slope of these tangent lines and they're increasing over time. And then if I have a linear velocity versus time graph, it means that the acceleration is constant, right? Because the slope of the tangent lines of this graph represent the instantaneous acceleration and they're not changing, so the acceleration is constant. And you could have a situation, although we won't see this in lab this week, but we could have a velocity versus time graph that is also, the graph is curved, right? It's not linear. And what does that mean? It means that the acceleration, so the slope of this tangent line would be the instantaneous acceleration at this time, and this would be the instantaneous acceleration at this time. The acceleration itself is changing, right? The acceleration is actually increasing in this case, right? But we're just going to deal with, at least in this lab, with constant accelerated motion. Okay, so here's the one other thing that that we need, one formula that I used in the table, and you guys will have to compute these things with this formula. So it turns out, and it'll help if you watch this video to see what's going on. So I created a brief video explaining how I collected all the data for the tables. So in the constant acceleration part, we start the cart at rest right before it triggers the photo gate. So it's Vx initial is going to be 0. It's starting at rest right before it triggers a photo gate. We release it, the flag passes through the photo gate. You can think of the flag as being sort of like, it sort of represents the displacement of the cart, right? So it moves that amount, 10 centimeters, 15 centimeters, whatever it is, it moves the length of the flag and recording the time it takes the flag to pass through. Well, in the second part of the experiment, when we look at acceleration, we want to calculate the final velocity of the cart as the end of the flag passes through. So after it undergoes, you know, a 10 centimeter displacement or a 15 centimeter displacement, whatever it may be, we want to find that final velocity. So the way that we do that is the following. There's two ways that we can represent the average velocity. Because we have constant acceleration, it turns out that the average velocity is simply going to be the average of the initial and final velocities. Okay. And then the second way that we can represent the average velocity is by the definition. So I defined it first as being change in position, right? Delta x over change in time over delta t. So if I set these two expressions equal, so this expression I set equal to this expression, which I did right here. We know that the cart is starting at rest, so Vx initial is 0. Remember, I want to solve for Vx final. So all I need to do now is multiply both sides of the equation by 2, and that's going to be my answer here. So Vx final, the final velocity of the cart as the end of the flag passes through, is 2 times delta x over delta t. So it's basically twice the average velocity. And again, this is only true because the cart is starting at rest and it's undergoing constant acceleration. If that's the case, then it is always going to be true that the final velocity is going to be twice the average velocity. Okay, you will need that to do some of the calculations later. So you have that. But again, watch my brief little video, and it'll make more sense when you actually see what's going on with the air track. Okay, so in terms of the questions, so again, all 3 classes are gonna do this part of the experiment. So I recorded the time it took the flag, the different flag lengths. So these are the 5 different flag lengths: 10 centimeters, 15, 20, 25, and 30. And these are the times in seconds that it took that flag to pass through the photo gate. And in this case, the cart is on a flat air track. So it's on a horizontal flat air track. And when I launch it with a rubber band launcher, I launch it consistently so it has the same velocity every time, or as best I can. Of course, I can't get it exactly the same, but I tried to make it so that it had a very similar velocity every time. And that was true regardless of the flag length, right? So what I want you guys to do, question 1, is to compute the average time. So just average these 5 values. Make sure you round it to 4 places. I would use all 4 places here. And then compute the average velocity, so delta x over delta t. So you can just do, in this, like for the first one, it would be 10 divided by this average time, right? And then 15 divided by this average time, and so on. And maybe round these to, like, say 2 decimal places, okay? So compute delta t, compute the average velocity. And then I want you to plot delta x versus delta t. So using Pascal capstone, plot position versus time. So what does that mean? It means that, and you gotta be careful here, delta t will go on the x-axis. That's sort of the independent variable. And then delta x, which is really our position, that's on the y-axis. So x and then y. Okay, once you have that graph, you can answer question 2. What is the shape of the graph? Perform a linear fit to the data. What is the value of the slope? So remember, when you do the linear fit, it'll give you that slope value. And what does that slope represent? Okay, so you want to answer all those questions. And here in this little table, you can put the slope value. Kind of giving you a hint by giving you units, right? It's centimeters per second. It's going to be the slope. Okay, next, you want to graph the average velocity versus time. So if you look back in the table here, delta t is going to be on the x again, and now average velocity delta x over delta t will be on the y. So it'll be x this column and then y this column. And for this graph, this is the only graph where we don't want to include 0, 0. It doesn't make sense to include 0, 0. The other graphs you can include the 0, 0. But in this graph, we don't want to include 0, 0. Okay, for question 3 here. Now, there's a few things you need to do here. So let me jump on Pascal capstone to kind of show you how to do this. Because it turns out that it should be a horizontal graph. Okay, let me get on Pascal capstone and show you that. Okay, so here is capstone. We're going to go to our usual, the upper left-hand icon. So in this case, I'm going to plot time. Now remember, you don't want to use the word time because it doesn't like that. It's the default name and it gives us problems. So just call it like time2 or time underscore or something. I'll call it time2. And that'll be in seconds. And then I want to plot my average velocity on the y. Okay, so I'm going to make up some data here. Let's say my times were, actually, this is the one I don't want to use 0, right? So I'll say 1, 2, 3, 4, 5. And what you guys are going to find is that your average velocity should be pretty consistent, right? It should be about the same. So remember, we're in this part of the experiment, we're hoping that the cart is undergoing constant velocity. It won't be exact, but let's say my values were like 25, 24.5, 26, 24, 25. Okay, so on the x-axis, I'll plot time. So time2. On the y-axis, I'm going to plot average velocity. Now, even though my values are very similar, it doesn't look horizontal, right? It doesn't look flat. And it's because it zoomed in, right? It's scaling this. So we can fix that. Here's what you need to do for this particular graph. First of all, get rid of the line segment connections as usual. So I'll highlight a point, right click, unconnect, show connecting lines. Then I'm going to go over to the y-axis, like anywhere, kind of where you see that double arrow there. I'll right click, go to axis properties, axis scaling, and then I'm going to change the maximum and minimum value. Let's make the minimum value just 0. And then since my highest data point was what, like 26, let's go to like 30 or something. That should be good. So maximum would be 30. Okay. All right, great. So now now it looks like it's pretty much constant, pretty much horizontal. So the way that we do that, that fit there is you're just going to do, instead of using the fit, because there is no constant fit, we're going to use this average here. So this is like the sigma button, like for statistics. If you click on that, it should give you a mean, which is going to be the average of your values. And that's what you want. And then don't forget the title, right? So this would be like average velocity versus time. Great, so you should find that this average here represents your constant velocity. And in particular, it should be very close to being the same value as the slope from the first graph. Remember, the first graph was position versus time, which should be linear. And that slope of the first graph should be very close to this average, right? Because they both represent the same thing. They represent the fact that that cart was moving at constant velocity. All right, great. And then you can do the usual, right? Copy and paste this into your lab report. Okay, so again, question 3, you want to do that plot, average velocity versus time. You can record that mean value, right? When you hit the sigma button, the statistics, record that mean value. And then answer this question, how does that compare to the slope from question 2? Well, they should be very close, right? Because they both represent the fact that the cart should be moving at constant velocity. Okay, the next part is the constant acceleration part. And again, all 3 labs will do this. There's one question at the end that Physics206 doesn't have to answer, and I'll show you that when we get there. So here's the data table. This is when the air track was on an incline, so the cart underwent an acceleration. And again, I got these values by starting the cart so that the flag was just ready to trigger the photo gate. I released it, it accelerated down, and these are the times it took the flag to pass through the photo gate for each of those flag lengths again, for the 5 flag lengths. So for the 10, 15, 20, 25, and 30 centimeter flag lengths. Okay, so what I want you to do is question 4, compute the average time. This column is going to be the average time. Make sure you round to 4 decimal places. And then compute the final velocity. Remember, the final velocity we derive from that formula. It's going to be twice, don't forget the 2 here, that's important, twice the average velocity. So if you do like delta x, say for the first one, it'd be 10 divided by this average time, that would be average velocity, and then times 2 will give you the final velocity. And then 15 divided by this time times 2, and so on. So you should be getting these final velocities here. Now, just eyeballing it, what should be true about these values? Well, these values, right, as time goes on, right, as the cart is accelerating for a longer time, that final velocity should be getting larger, right? So these values should be increasing. So good check is to make sure that these values are increasing. Whereas in the first experiment, the average velocities, these should be pretty much constant, right? Pretty much the same for all 5 values. But in the second part, these should be increasing, right? The final velocity should be increasing. Okay. Once you have that, you want to plot position versus time. So time is going to be on your x-axis, and delta x, which is your position or change in position, but think of it as position, is going to be on your y-axis. So y x, and make sure you include 0, 0. What is the shape of your graph? Well, if you think about this, right, what should the shape be? I'm plotting position versus time, and I know that my car is accelerating, which means its velocity is changing, right? It's increasing as I go down the air track. So that means the slope of the graph must be increasing. Okay, so if you think about that, it should make sense when you do that plot. Question 5, plot final velocity versus time. So now this will be, time is always x for all these graphs. So time is x again, and now the final is going to be your y. Include 0, 0. Do the plot. What is the shape of the graph? Well, think about it. Remember, in this case, the cart should be undergoing a constant acceleration. So if you plot velocity versus time, it undergoes constant acceleration. What should that graph look like? I kind of give you a hint here by telling you to perform a linear fit to the data. Record that slope value, and what does that slope value represent? Again, the unit should give you a hint here, right? The slope is in centimeters per second squared. Okay, so basically there's four graphs that you need to do, right, for this part of the experiment. Now, for the next part, this is going to be question 6, and only sections 207 and our classes 207 and Physics 212 have to do this. 206, you don't have to worry about this particular question, okay? So in this case, we're going to theoretically compute the acceleration of that cart as it goes down the air track. So here's my free body diagram. I have two forces acting on that cart, right? The reason why we use the air track is to make it friction negligible. So basically we can assume there's no frictional force here. So the only two forces acting are the weight, which is acting down towards the center of the earth, right? So that's mg. And then the normal force, which is the force that the surface exerts on the cart perpendicular to the surface. So it acts like this. And then the angle that the air track makes with the horizontal it turns out to be the same as this angle right here that the weight makes with a line that's perpendicular to the track. So this angle theta is the same as that angle theta. So if we look at what's going on in the x direction, think of, and I oriented my coordinate system so the x just goes down the air track, right? And y is perpendicular to the air track. So because we know the acceleration is occurring in the x direction, right? Nothing's happening in the y direction. The cart is not leaving the air track at all. It's just accelerating down the air track. So we can think of it as moving just in the x direction if I orient my coordinate system like that. Well, what is the component of the forces in the x direction? Well, the normal force, right? Its component in the x direction is 0, right? There is no component in the x, it's all in the y. Now, the weight here, part of it is in the x direction, and it's just a small part. In fact, it's going to be the weight times the sine of theta. Let me show you this here. I'll do this part on the iPad to explain this more carefully. Okay, so in this case, I have the air track. It makes an angle theta with the horizontal. And I have the cart. And it has two forces acting, right? It has the weight, which is acting down. So this is mg. And it has the normal force acting perpendicular to the track. And then I'm going to draw my coordinate system like this. So I have x, y, because I know that the cart is accelerating down in the x direction. It's just easier to use that coordinate system. And it turns out that this angle right here is the same as theta, same as the angle that the air track makes with the bench, with the horizontal. Okay, so I want to find the x components of my two forces. Well, first of all, if you project the weight onto the x-axis, it'll be something like this. So it's this value right here. I'll call this Wx. And if I project it onto the y-axis, this is going to be the y component of the weight. So if you want, you can extract out that triangle. So this is my right triangle, right? This is theta. This is Wy. This is Wx. And this is W, which is mg. So the hypotenuse is basically mg in this case. So how do I find Wx and Wy? Well, relative to theta, what is Wx? It's opposite, right? So we could say that sine of theta is equal to the opposite over hypotenuse. And then if I want to solve for Wx, I can multiply both sides by mg. So I'm going to find that Wx is mg sine theta. And then for the y, I can use, since Wy is adjacent to the angle, I know that cosine of theta must equal the adjacent side divided by the hypotenuse. So therefore, Wy must be mg cosine of theta. Okay, now if we apply Newton's second law in both directions, so let me do the y first. That's the one actually we don't care about too much, but I'll do that first. So if I do sum of the forces in the y, that's got to equal ma(y). So I have two forces, right? I have tension, I have normal force and I have the weight. So I want the y component of the normal force plus the y component of the weight. That's got to equal ma(y). But if you look back at the picture, how much of the normal force is acting in the y direction? All of it, right? In fact, really, if I'm being careful, this is a vector, right? That's a vector, and this is a vector. So the y component of the normal force is all of n. And then how much of the weight is acting in the y? Well, we found the Wy component, and it's acting in a negative direction. So this would be negative, and remember, it's going to be mg cosine of theta. And that's got to equal ma(y). But what is the acceleration in the y direction? Well, since the cart is not moving off of the air track, the acceleration in the y direction is 0, right? ay is equal to 0. I'll write that here, ay is 0, right? Because it's not jumping off the air track at all. So therefore, this tells us that the normal force is equal to mg cosine theta, which is true, but not really helpful. If there were friction, this would be very useful because friction depends on the normal force. But in this case, it's just a true statement, but it's not what we want. We really want to find the acceleration down the air track. So we want to find the acceleration in the x direction. So I can do that by using Newton's second law again, but now I'm going to look at the x direction. So now I have sum of the forces in the x equals max. So now I want the x component of the normal force plus the x component of the weight. That's got to equal max. Well, what is the x component of the normal force? So again, if we look at the free body diagram, how much of that normal force is in the x direction? None of it, right? It has no component in the x direction. So that's 0. How much of the weight is in the x? Well, we already figured it out. It's going to be mg sine theta, and it's positive. So that's got to equal max. And now, of course, we can divide both sides by m, so I can get rid of the m. So it turns out that the acceleration that we want, ax, is simply going to be g sine theta. So g sine theta. So how do we find sine theta? It's not really easy to measure the angle theta. So what we're going to do is we're going to measure the height of the air track at both ends, and that will allow us to compute theta. Okay, so let me go to the next page and show you that part. So again, we found that the acceleration should be g sine theta. But let's say that this is the air track. And we know its length, right? It's like a 2-meter air track, so that's 200 centimeters since we're using CGS units. And let's say that this is height 2, and this is height 1. I forgot which way I did it in my notes. Hopefully this is the same way as my notes, but I'll call it height 2. So the larger height is height 2, and smaller is height 1. And this is my angle again, my angle theta. So it turns out that this distance right here is simply h2 minus h1, right? It's the difference in the heights. And using trigonometry again, so if we use trigonometry just on this triangle, then we can see that the sine of theta is going to be opposite. So the length of the opposite side is h2 minus h1 over the hypotenuse, and that was a 200 centimeters. So now we can simplify our formula for the acceleration, right? It's going to be, it's g sine theta, but we know that sine theta is simply h2 minus h1 over 200. Okay, so the h's have to be in centimeters. The g is going to be 980 centimeters per second squared. And that will allow you to calculate the theoretical acceleration. All right, let me go back to the handout. Okay, so actually I just did most of that work here. And we found that ultimately, right, to figure out the acceleration, the theoretical acceleration, it's going to be g, which is 980, times sine theta, but sine theta you can write as h2 minus h1 over 200. So I measured the heights for you. So h1 is 11.2 centimeters, h2 is 20 centimeters, so you have those. So you just need to answer question 6. So find the theoretical value of the acceleration from this formula. That'll be this answer right here. And then compare it to the experimental value. And where does that come from? It comes from that last graph that you did when you graphed velocity versus time, right? Final velocity versus time. Remember, the slope of that graph represented the acceleration. So this comes from the graph. So this is from the slope of the graph. And you want to compare these two by computing a percent experimental error. And again, make sure you show me all of these calculations, right? Show me the calculations for your lab report. Okay, great. So that's it for the first part of the lab. Now, part B is graphical interpretation. So what I'm going to do, and I even make a note here, make sure you look at the graphical interpretation practice sheets before attempting the remainder of the lab. I'm going to walk you through some of these practice sheets. What we're doing is we're looking at position versus time and velocity versus time graphs and trying to answer questions based on those graphs. Okay, so let me go to the practice before I show you, your particular lab report. Okay, so this is the first practice sheet on the graphical interpretation. And I want to walk through a bunch of examples so you'll have a good idea of how to actually answer the questions for your lab report. So this is a graph of position versus time. And notice that there's a couple of strange things here. First of all, at these times here, it's sort of like a kink here where you're going from like, you know, a positive velocity to zero velocity instantly. And we know in reality, you can't do that. Usually all these little kinks here would be nice and smooth, but for teaching purposes, it's easier to draw it like this. So that's why I did it. That's why I call these graphs sort of like idealized graphs, okay? So you kind of have to ignore what's going on right there at these little kinks, right? Normally it would be smoother, but then it becomes a lot more complicated. All right, so if we're given a position versus time graph and we're asked a question about position, then we can read the answer directly from the graph, right? So if I'm given position versus time, I'm asked a question about position, I can read the answer directly off of the graph. If I'm given a position versus time graph and I'm asked a question about the velocity, then what you want to look at is the slope, right? Because remember, the slope of the tangent line represents the instantaneous velocity. So if we look at the slope of the position versus time graph, that tells us about velocity. So I'm going to walk through this, and I'll try to do this on the iPad. I think it'll be easier. And I have a bunch of questions that I want to ask about this particular graph. All right, so let me go to the iPad. Okay, so here's the graph, position versus time graph. And the first question is, what is the particle's position at 3 seconds? First of all, even before I start this, I should let you guys make sure you understand what's going on here. This is one-dimensional motion, right? This is just a particle moving. Think of it as moving along the x direction. It's either moving to the right or to the left. So it's moving along the x direction, maybe at different speeds, but either to the right or to the left, okay? So the first question is, what is the particle's position at 3 seconds? So since I have oh, hold on one second. I think I have the wrong graph here. Okay, sorry about that. I was reading the wrong handout. So the first question is, what is the position of the particle at 1 second? Okay, so since I have position versus time, to answer that question, I go to 1 second, right there. I go up to the graph, and then I can read off that value, right? The value is 1 meter. So the position of the particle at 1 second would be 1 meter. Okay, the next question is, what is the velocity of the particle at time 5.5 seconds? Okay, so to answer that, right, I would go to 5.5 seconds. I have to go up to the graph. And since I want the velocity, I want the slope of the tangent line that touches the graph at that instant, right? So if I draw this, let me draw a tangent line in there. So something like this, right, just touches. Now notice that the slope of that tangent line is the same as the slope of the entire line because it's really constant velocity over that entire time interval from 4.5 to 6.5 seconds. So if I want to find the slope of just that blue tangent line, really it's easier just to find the slope of the entire line, right? So if I choose, say, the two endpoints, let me choose, say, this point right here, right, which is 4.5 comma 4, and then this point right here, which is 6.5 comma -2. And then I can calculate the slope of that entire line, and that will also be what I want, right? That's going to be the same as the slope of that blue tangent line. So how do I find that slope? Well, remember, it's going to be the change in position over the change in time, right? So in this case, actually, it'll be, you can think of this as, say this is T1, X1, and then I'll call this T2, x2, right? So it's going to be x2 minus x1 over t2 minus t1. So in this case, it would be negative 2 minus 4 over 6.5 minus 4.5. Negative 2 minus 4 is negative 6. 6.5 minus 4.5 is 2. So this is going to be negative 3, right? Meters per second. So the slope of that entire line, which is the same as the slope of what we really want is just the line segment right at 5.5 seconds, is going to be negative 3. So the answer to that question would be negative 3 meters per second. Okay. And in the future, you don't even really need to write out all these points. You can just look at this, right? And think about it as being rise over run. So if I start at 4 on the y and I go down to negative 2, that means my rise is a negative 6. And my run, if I go from 4.5 to 6.5, my run is a positive 2. So negative 6 divided by positive 2 is negative 3, right? It's the same thing, but you can just think about it quickly as rise over run. You don't have to even do much of the math out. Most of this you can do in your head. Okay, what about the next question? It's question C. Is the particle ever moving backwards? Well, how do we know if it's moving backwards? It'd be moving backwards if the slope is negative, right? Because the velocity tells us the direction. If the velocity is positive, it's moving in the positive x direction. If the velocity is negative, it's moving in the negative or backwards x direction. So it's only when the velocity is negative is it moving backwards. And graphically, that means the slope has to be negative. So where is it moving backwards? Well, actually, it's exactly over the interval we just looked at, right? It's moving backwards from 4.5 to 6.5 seconds over that interval because the slope is negative. Everywhere else, the slope is positive, 0, positive. It's only here the slope is negative. Okay, over what interval is the speed of the particle the greatest? Well, the speed is the magnitude of the velocity. So it doesn't care about the sign. It doesn't care if we're moving forward or backwards, right? It's just the magnitude of the velocity. So how do I figure out the location where I have the greatest speed? Well, it's going to be the location where we have the greatest slope, right? So you could eyeball this, or you could actually calculate all these slopes, but it turns out, again, the steepest slope is again from 4.5 to 6.5 seconds. In fact, the speed will be 3, right? Because remember, it's absolute value. Speed doesn't care about the sign. The velocity is negative 3, but the speed is 3. And that's going to be the greatest speed over any of these time intervals. Here it looks pretty steep too, but this turns out to be just 2, right? So 4.5 to 6.5 would be the answer. Is the particle ever at rest? Okay, so what does it mean to be at rest? It means the velocity must be 0, right? Graphically, how do I know if the velocity is 0? By looking at my position versus time graph. It's when the slope is 0, right? When the slope is flat. So the velocity, or this is 0, the particle's at rest between 2 and 3 seconds here, and also between 6.5 and 8 seconds right here. And again, we're ignoring, it turns out really up here, it'd have to be curved at some point, and then it would really be 0 in reality. But the way I have it drawn, it's kind of jumping from a positive velocity immediately to a negative. Now I know that that can't happen in reality, but it's easier in terms of teaching, okay? So we'll just say that it's at rest over this time interval, so 2 to 3 seconds, and over this time interval from 6.5 to 8 seconds. In what direction is the particle moving at 4 seconds? Okay, so I go to 4, I go up to the graph, I look at the slope. Remember, the slope tells me, so at that point, the slope kind of looks like this. It tells me the instantaneous velocity. The velocity will tell me the direction. And we know in this case it's positive, right? So you could say it's moving in the positive direction or forward direction, right? Because we have a positive velocity, positive slope. Okay, the next thing that we want to do is, given this position versus time graph, we want to sketch the corresponding velocity versus time graph. All right, so let me bring that up. Okay, so we want to sketch the corresponding velocity versus time graph given that initial position versus time graph. All right, so let's see if we can figure out what the velocity is from 0 to 2 seconds. Well, we know it's constant, right? Because it's linear, so it's constant velocity. And I can figure it out by looking at the rise over the run, right? So the rise, well, it's going from 0 to 2, so the rise is a 2. In the run, it's going from 0 to 2 as well, so the run is also 2. So 2 divided by 2 is 1. So the velocity must be 1 meter per second. So if I go to the graph, I'll do this in red. From 0 to 2, it's going to be 1 meter per second, something like that. Okay, what about from 2 to 3? Well, from 2 to 3, what's my velocity? It's 0, right? Because the slope is 0. Remember, the slope gives us the velocity. So the slope is 0. So if I go back to here, from 2 to 3 seconds, this is just going to be 0. And again, because it's an idealized graph, it really does jump, right? The graph, it doesn't, you don't connect the one, from 1 to 0. It jumps from here down to here. In reality, I know that can't happen, but with these idealized graphs, that's what is going on. It's actually jumping. Okay, what about from 3 to 4.5? Okay, so 3 to 4.5. My rise, well, it's going from 2 to 4, so that's a positive 2. My run, it's going from 3 to 4.5, so that's 1.5. So what's 2 divided by 1.5? Why, what's that, 4/3, I believe? So 4/3 should be the slope. So around 4/3 is like 1 1/3. So something like this. Okay, what about from 4.5 to 6.5? Well, that's the one we already calculated, right? What's the velocity from 4.5 to 6.5? It's -3. So 4.5 to 6.5 was -3. From 6.5 to 8, well, it's flat there, right? So the velocity must be 0. So something like that. And then finally, from 8 to 9, well, the rise, so it's going from -2 to +0. So the rise is a +2. The run is, it's going from 8 to 9. The run is a +1. So 2 divided by 1 is 2. So this is going to be +2. Okay, so that would be the corresponding velocity versus time graph. Okay, let's look at the next position versus time graph. Okay, so here's our next position versus time graph. So let's see if we can answer these questions. What is the position of the particle at 5 seconds? So I go to 5 seconds, I want to know the position, so I just read it directly off the graph, and it looks like it's 16 meters. So 16 meters would be the answer. Over what interval, if any, is the particle accelerating? Okay, now again, we're going to ignore, in reality, it would have to be accelerating where these kinks are at 1 second and 8 seconds, but we're going to ignore those. So what does it mean for something to be accelerating? It means its velocity must be changing somehow, right? And if I have a position versus time graph, what does it mean for the velocity to be changing? It must mean that the graph is curved, right? The slope must be changing because the slope represents the velocity of the position versus time graph. So where is the slope changing? Well, actually from 4 to 6 seconds, right? Initially, it starts off positive, then it gets small. It's still positive, but smaller, smaller, then kind of 0, negative, more negative. So it's curved over that time interval from 4 to 6 seconds. So that's where the particle is accelerating. Okay, and I'll explain that a little more carefully in one of the later questions. Is the particle ever at rest? Yeah, it's where the slope is 0, right? So definitely between 0 and 1 second. Definitely between 8 and 12 seconds, right, where it's flat. And actually right at 5 seconds, if you were to do a tangent line there, it's at rest just for an instant, right? It has 0 velocity for an instant right at 5 seconds. What is the velocity of the particle at 4 seconds? Okay, so I go to 4, I go up to the graph, I want the velocity, so I want the slope of that line. Well, right at 4 seconds, that's basically the slope of this line, right? It hasn't changed. Right after 4 seconds, it starts decreasing, but right at 4 seconds, it's still the same slope of this line. So if I can figure out the slope of this line, then I have my answer. Well, we can figure it out by looking at rise over run, right? If I go from this point to this point. So I'm going from 2 to 14. So my rise is 12. And my run, I'm going from 1 to 4, right? So my run is 3. 12 divided by 3 is going to be 4 meters per second. So in fact, throughout the entire interval from 1 to 4, my velocity is 4 meters per second, and then it starts decreasing after that. Okay, what direction is the particle moving at 5.5 seconds? So I go to 5.5, go up to the graph, draw a tangent line. So something like this. And because the slope is negative, it means the velocity is negative. Therefore, it's moving backwards or in a negative direction. Okay, and then the last question is, what is happening to the velocity of the particle between 4 and 6 seconds? So again, at 4 seconds, right, at 4 seconds, we know that the velocity is 4 meters per second. Then as time goes on, the slope is becoming less steep, less steep. Right at 5 seconds, the slope is 0. Then it becomes negative, right? Small negative, then more negative, and eventually, right at 6 seconds, it's at -4. So the velocity is changing from +4, going down to 0, and then it's going negative direction now from 0 to -4. Right? So the velocity is changing over that entire time interval. All right, now we want to draw the corresponding velocity versus time graph. Okay, so from 0 to 1 seconds, what is the velocity here? Well, we know it's 0, right? Because the slope is 0. So on this page, from 0 to 1, it is 0. Something like that. What about from 1 to 4? Well, from 1 to 4, we already calculated that, right? That slope is going to be 4 meters per second. So from 1 to 4, it'll be 4 meters per second like this. Okay, here's the tricky part. What about from 4 to 6? Well, we know right at 4, it's 4 meters per second. Then it starts decreasing at 5, right? At 5, it's 0. And then at 6, it's -4. The slope is -4 because this is -4 right here. So it goes from 4, it decreases to 0 at 5, and then -4 at 6. So how do I draw that? Well, again, we know that at 4, it's still 4. At 5, it's 0. And at 6, it's -4. We know it's decreasing. And our best guess, right? We don't know this exactly. Well, I do because I made up the data and I know it's quadratic. So I know that the velocity has to be linear. But we know that it must be decreasing somehow. So your best guess is just to draw it as linearly decreasing. So it does something like this, right? It decreases to 0. Then it becomes negative, right? Small negative at first and more negative all the way down to -4. You guys see that? So it started at 0. It got less positive, right? Say 3, 2, 1, 0. Start at 4, 3, 2, 1, 0 at 5 seconds. So 4, 3, 2, 1, 0 at 5 seconds. And then it becomes small negative, more negative, more negative, more negative until it's -4 at 6 seconds. So negative, let's say -1, -2, -3 to -4 at 6 seconds. Okay, from 6 to 8, that slope is -4, right? It's constant at -4. So something like that. And then finally, from 8 to 12, that's easy. What is the velocity from 8 to 12? It's 0, right? Because that's at rest. So this would be 0. Okay, let's look at the next practice, which has a velocity versus time graph. Okay, so here's my velocity versus time graph. So now this is a little bit different. So if I'm asked a question about the velocity, I can read it directly off of the graph, right? Just read it directly off the graph because I have velocity versus time. If I'm asked a question about the acceleration, that's when I want to look at the slope of the velocity versus time graph. And then finally, the one that I need to talk a little bit about more, if I'm asked a question about the displacement, like the change in position, then I want to look at the area underneath the velocity versus time graph. So if I'm asked about velocity, just read it directly off of the graph. Acceleration, look at the slope. If I'm asked about change in position or displacement, I want to look at the area underneath the velocity versus time graph. All right, so let's see if we can answer these questions. What is the velocity of the particle at 3 seconds? Okay, so I'm asked about velocity directly. So I go to 3 seconds. I just go up to the graph. I read off the value. It looks like it's 4 meters per second. Right? Can answer that directly. During which time interval or intervals is the velocity of the particle positive? When is it moving in the forward direction? Okay, now you have to be careful here, right? It's easy to make this mistake. I've made it myself many times. If this were position versus time, then the slope matters, right? Like we would say, since this is a positive slope, oh, it must be moving positive, and this is negative, must be moving negative. But this is not position versus time. This is velocity versus time. So if you look at the velocity, see how it's at like 6 meters a second, then it decreases to like 2, but it's still moving forward, right? It's still moving at a positive 2. Then it goes up to, say, what is that, 10, and then down to 8. But it's always moving in a positive direction. The only way that this could be negative is if this drops below 0. And actually, it could only be at rest if this graph actually goes to 0, right? And it would have to be negative for it to be moving in the backwards direction. But in this case, it's always positive. So it's always moving in the forward direction for this particular example. So that kind of answers the next questions, right? During which time interval is the velocity of the particle negative? Never in this example, right, with this graph. And is the particle ever at rest? No, never in this graph, because it'd have to go down to 0 to be at rest. What is the acceleration at 10 seconds? So I'm asked about acceleration, so I go to 10 seconds, go up to the graph. Since it's velocity versus time, I want to know the acceleration. I want to know the slope of the tangent line right at that point. But that's the same as the slope of this entire line because it happens to be constant acceleration over that time interval. So I just need to calculate the slope of that line. So let's see, it's going from 10 to 8. So that is a -2, right? So -2 is a rise. And then 9 to 11, so that's +2. So -2 divided by +2 is -1 meters per second squared. Okay, during which time interval is the magnitude of the acceleration the greatest? Well, magnitude doesn't care about whether it's positive or negative, right? It's absolute value. So I'm looking for the interval where I have the greatest slope. It doesn't matter if it's positive or negative. That will give me the greatest magnitude of the acceleration. And it turns out in this case, if you do all these, well, this is 0, right? This is some negative, some positive, some negative. But I just want the greatest, the absolute value. So it turns out between 2 and 4 seconds, I have the greatest magnitude of the acceleration. It happens to be negative acceleration, but it's the greatest magnitude. Okay, the next question deals with displacement. So it says, what is the particle's displacement over the first 4 seconds? All right, so remember I said earlier, if we want to find displacement, displacement is going to involve finding the area underneath the velocity versus time graph. Why is that? Well, let's think about this a little bit. So if I have, here, let me give you remember the definition of average velocity is change in displacement, right? Or change in position, which is displacement, divided by change in time. If I rearrange this, I can write my delta x, my displacement, as average velocity times time, times delta t. So look what's happening here. If I want to know the displacement from 0 to 4 seconds, right? Then I know it's going to be a velocity times a time. So let's let's start by looking at just from 0 to 2 seconds to start with. Okay, so just this part right here. So I'll kind of block this off. So this right here is my velocity, right? This is like, in fact, it's constant there. So I could say this is like my v_av, which is 6. And then this would be my delta t. But if I multiply those together, because it's saying that delta x here is v_av times delta t, isn't that just the area? Right, the area of that rectangle? So if I want to know the displacement over the first 4 seconds, I have to add up all the areas underneath the velocity versus time graph. So basically, think of this as, I'll call this like area 1, say area 2, area 3. Okay, and if I add up those 3 areas, that must be my displacement over the first 4 seconds. So how do I find area 1? Well, that's a nice easy shape, right? It's a rectangle. So area 1 is going to be length times width. So that'll be the velocity, which is 6. That's my length, right? The height there, times the time, which is 2 seconds, and that's going to be 12 meters, right? The seconds will cancel. Meters per second times seconds is meters. For area 2, that's the area of a triangle. Remember, the area of a triangle is 1/2 base times height. So I could say base times height divided by 2. So my base in this case would be this, right? And the height would be this. So the base is 2. It's basically 2 seconds. Times the height is 4 meters per second divided by 2. So this is going to be 8 divided by 2, which is 4 meters. Okay, so that's that area right in here. And then finally, A3 is just another rectangle. So length times width. And that turns out to be, it looks like 2 meters per second times 2 seconds. So that's also going to be 4 meters. So then my displacement over the first 4 seconds, graphically, I can get it just by adding those areas. A1 plus A2 plus A3. And so that would be 12 meters plus 4 meters plus 4 meters. So that's going to be 20 meters. Okay. And then if you wanted to calculate the area or the displacement over the entire 11 seconds, then you'd have to, maybe break this up into a rectangle here, or sorry, a triangle there, a rectangle here in the bottom, maybe a little triangle there, and then a big rectangle there. And if you add up all those areas, that will give you the total displacement over the entire 11 seconds. Okay, what if the velocity becomes negative? Like, what if you have something like this? So what if it were, I don't know, something like that, over the time period? Then if you add up this area, it's going to be a positive displacement, right? Because it's moving to the right, it's positive velocity is moving to the right. And then this area, since the velocity is negative, means it's moving backwards, it would be a negative displacement. So you'd have to add that area and subtract out the area beneath the time axis. Right? So anything that's positive would be added, right? It'd be a positive displacement. And anything below, when the velocity is negative, that's going to contribute a negative displacement. It's moving backwards in the other direction. Okay, so that's important. Another thing is, what if the graph is really complicated, right? What if you can't break it up into nice, easy rectangles and triangles? So what if you have something like this? Let's say that's my velocity, right, over time. And I want to estimate the displacement over that time period. Well, it's not very easy, right? If you know calculus and you knew this function, so if you actually knew the function of that curve there, then you could do what's called integration. You could integrate, and that would give you the area underneath the curve. So that's one way to do it if you happen to know calculus. But one way you could estimate it graphically is you could break this up into like little squares. Like you could say, well, let's say over this time interval right here, let me just break this up into little time intervals. So over that time interval, since it's probably the average is probably like halfway in between, maybe something like this. Over this time interval, maybe it's something like that, and so on. And I can calculate these are just rectangles, right? So if I know that value, that height, I can find that little displacement, and so on. And I can add all these up, and that will give me the total displacement. So that, of course, there's going to be a little bit of error, but the smaller you make those rectangles, the smaller the error. Right? So it gives you an estimate of what the displacement would be if you break it up into like little rectangles. And then if you get more advanced, you could break it up into like trapezoids and things like that. In fact, that's what a computer does when it estimates what the area underneath the curve is. It breaks it up into small trapezoids or rectangles. And if you make it smaller and smaller and smaller, it becomes more and more accurate. Okay. And I will give you guys a chance to do that in a couple of the questions. Okay, the last thing I want to do for this practice is let's come up, so this was our velocity versus time graph. let's come up with a corresponding acceleration versus time graph. So if I look at the first 2 seconds, so 0 to 2, what is the acceleration? Well, the acceleration is the slope, right? So the slope over the first 2 seconds is 0. So here, when I go to acceleration, over the first 2 seconds, I know the slope is 0. So it's something like that. All right, what about from 2 to 4 seconds? So 2 to 4, well, my rise, it's going from 6 to 2, so it's a -4 over, my run is a +2, so -4 over 2 is a -2. So something like this. Then from 4 to 9, well, it's going from 2 to 10, so that's 8. And then my run is 4 to 9, so 5, so 8/5. So what is that, 1.6 about? So 8/5, right, or 1.6. That's all the way to 9. So something like that. And then finally, what's my acceleration from 9 to 11? Well, my rise, it's going from 10 to 8, so -2 over my run is +2, so that's a -1. So -1. So that would be the corresponding acceleration versus time graph. Okay, so that should give you an idea of how to answer these questions. So let me just walk through the questions, and then that'll be it for this particular lab. Okay, so to start, I give you a position versus time graph. I want you to answer the questions based on that particular graph, okay? And you can just put in the answers in the blank spaces here, and then just attach all this to your lab report, or copy and paste it into your particular lab report. Okay, so position versus time, and there's several questions involving that graph. Then question 8 is draw the corresponding velocity versus time graph. So based on this position versus time graph, draw the corresponding velocity versus time graph. Then question 9, I give you another position versus time graph. Again, answer the questions. This is a little more complicated because it's curved here. So remember, it's accelerating from 0 to 4 seconds. It's curved. But otherwise, it's not bad. You can always ignore where there's kinks, right? You don't have to say it's accelerating where there's kinks. Just from 0 to 4 seconds, it's accelerating here. So answer those questions and draw the corresponding velocity versus time graph. Then I give you a velocity versus time graph, okay? Answer the questions based on that velocity versus time graph, and then draw the corresponding acceleration versus time graph. Okay, and actually, if you're in Physics 206, that's all you have to do, so you can end it there. If you're in Physics 207 or 212, you want to also do this question. So I'll give you another velocity versus time graph, a little more complicated because it becomes negative, right, at some point. So I want you to answer the questions based on that velocity versus time graph. Then this question, question 14, again, both classes 207 and 212 will answer this question. I give you 3 graphs. One is acceleration versus time, one's velocity versus time, one's position versus time. They don't correspond to the same motion, okay? So they're not acceleration, velocity, and time graphs of the same motion. They're different motions. But given these graphs, I want you to indicate the letters, so A, B, C, D, E, F, G, and so on, where the acceleration is 0, okay? So you have to think about it. If I have an acceleration versus time graph, what does it mean for the acceleration to be 0? If I have a velocity versus time graph, what does it mean for the acceleration to be 0? If I have a position versus time graph, what does it mean for the acceleration to be 0? And just give those letters here, okay? I'll give you a hint. There should be total 4 letters. So 4 letters total. All right, and then question 15, which is both for Physics 207 and 212. I want you to estimate the displacement. So I'll give you a velocity versus time graph. I want you to estimate displacement of the object by approximating the area using rectangles that are of width 1 second. So, and I started the process for you, right? So this is like, you know, a height of 1.5 times 1. So that would be my displacement over that first 1 second. Then I have to add the second rectangle. And since it's curved here, I'm kind of estimating around halfway. So like 2 to 3, you might want to go to maybe like, you know, 7 or something might work. Actually, where it's linear here, what you should do is from 3 to 4, you should go to say maybe 9, right? Because then what happens is I'm missing this little triangle, this little piece, but I'm including this piece and they cancel each other out. So the between 4 and 5 maybe go to 7, right? A height of 7 and so on. And then you're going to add up all those rectangles and that will be an estimate of the displacement over the entire 12 seconds. And don't forget in this part, so here you probably want to go to negative, let's see, it'd be -2, right? Because that would split it in half, -2. Here you can go all the way to -4. And these are going to be negative, right? So don't forget that these are going to be negative when you count these rectangles, these areas. So you're going to estimate the displacement by finding all those little areas of all the rectangles. Okay, and then the final few questions. So 207, that's as far as you have to go, question 15. 212 will do the rest of the questions as well. So here is a velocity versus time graph, a little more complicated. So I want you to answer the questions about that velocity versus time graph. Question 17 is, given this velocity versus time graph, give me the corresponding acceleration versus time graph. And then finally, question 18, I give you some information. I tell you that a car is traveling on a straight road, right? Think of it as traveling along the x direction in the positive, along the x-axis in the positive direction. It starts at rest at position x equals 0, accelerates for 10 seconds at a constant rate until it reaches a velocity of 30 meters per second. It then travels with 0 acceleration for 30 seconds. Finally, it decelerates for 10 seconds at a constant rate until it stops. Sketch the correct position versus time, velocity versus time, and acceleration versus time graphs of the car given that information. And my hint here is to start with the velocity graph. That's going to be the easiest one to get from the information. And then when you have the velocity graph, you can get acceleration just by looking at the slopes, right? And then you can get the position by looking at the area underneath the velocity versus time graph. So I would do the velocity versus time graph first, and you can figure out the rest of these. All right, so there's quite a bit for this lab. It's all about, you know, constant velocity, constant acceleration, motion, and interpreting graphs. A big part of this is interpreting graphs. All right, and if you guys have any questions, of course, feel free to let me know and I can help you out with any of this. All right, great, good luck.